Hello everyone, welcome to our discussion of section 9.2 where we will be talking about calculus with parametric curves. Now in section 9.1 we talked about parametric curves, which was really a review of the same topic that we had discussed in a trigonometry course or Math 127 if you took the course here. So here we talk about how we apply calculus methods to various situations that involve parametric curves. Now these various situations are, I've divided these into three cases. Case one being when a tangent line is given as a parametric equation, then we want to know the slope of that line. And we will apply a specific methods for that. And the second case would be if an equation of a line has been given in terms of parametric equations, which means involving a third variable time, then we want to know what methods, calculus methods, we can apply to such equations to calculate the area under such curve. And lastly, we will apply calculus to equations that have been given to us in terms of parametric equations, such that we want to calculate the arc length. So those are the three cases: calculation of the slope, which directly translates into calculating the equation of a line. If you know the slope, then you can calculate the equation of the tangent to that line at some specific point. Applying it to calculation of area and applying it to calculation of the arc length when the equation of the line is not in terms of just directly x and y, but we have a third variable involved. So here, as you can see on the screen, we begin with case one, which is calculating the slope of the tangent to a curve, and I've called it m, which is familiar to us from basic algebra, or dy dx, which is the calculus term or notation for that. So the way we calculate dy dx, if we have the equation of the line defined in terms of parametric equations like this, so x is given in terms of the third variable t, y is given in terms of the third variable t, and the way we calculate the slope of such line is by taking the derivative of y with respect to t, divided by taking the derivative of the x with respect to t. Now this is just the same formula we used in basic algebra. Remember the slope formula from Math 124 or college algebra, where we divided the difference between the y variables of 2 points along that line by the difference between the x values or the x coordinates. So this, of course, being calculus, we just don't always deal with linear equations. We have a lot of nonlinear curves where we will have to apply calculus methods for that. And this will apply only when we have x and y given to us in terms of a third variable. So we will apply that. Now, the curve has horizontal tangent at that point if dy dt is equal to 0. Okay, this should make great sense to you, because this is again connected to what we studied in basic algebra. So if the difference between the y components of a point of a pair of points on a line is 0, then we know that the line is horizontal. And so that's all that's saying is the same thing, but with calculus notations. And of course, this is being a new situation in calculus. Then the curve has vertical tangent when the denominator is 0. And again, from basic algebra, we knew that if we have an undefined slope, right? If this denominator is 0, then we have an undefined slope. So here we simply say that if that situation occurs, if the denominator is 0, which is dx dt, then we have a vertical tangent. Okay. or slope being undefined. Now here's something we studied in Calculus 1. We will use it here in this section. So I just wanted to remind you of it. If we have dy dx, then to calculate, the question is how do we get the second derivative if we need to with parametric equations? Well, all we have to do is really take the derivative of dy dx again, just like that. So d squared y over dx squared is take the derivative of, replace this y with dy dx, and the denominator stays the same. It's just divide by dx dt again. But just replace the y with dy dx, as I've shown in this box. Okay, we will apply these in problems that come up. Okay, so let us begin with a basic example and then work our way to more complicated examples. So here, all we have to do is calculate the slope, or dy dx, where we have the x and y given to us as parametric equations, right? So previously we had y equals some expression in terms of x, but now x and y are given in terms of a third variable t. So we want to apply the method that we just discussed. So we will use my ink already is dried, so we will use just this formula that we mentioned. Dy dx being equal to dy dt divided by dx dt. Okay, so and then so we have y equals that. I want to rewrite this so we have a rational exponent for instead of a square root of t. So let's rewrite it. Y equals t to 1/2 power times e to minus t. And then so now let's take the derivative of this expression, which would be the numerator in this expression. And we have 1/2 times t, reduce the power by 1, so we get minus 1/2 times, of course, e to negative t, and then plus the derivative of the second term, which is minus e to minus t power, times the term that came before it, so t to 1/2 power. So let's see, it looks like we can factor some things out. So e to the minus t power, we can factor that out. Also we have t to some power, so we will factor out the t variable with the lower power, so t to minus 1/2. We might as well factor out the 1/2 too. So factoring after factoring, we have this expression. One half, and then t to minus 1/2 power, and of course let's factor out e to minus t. Then for this, then to get this back, all we need is a 1. Factoring being the opposite of the distributive property, and then to get this plus, and so we minus, actually minus here, so we have minus, and then we have, all we need is a 2 first of all to cancel the effect of this 1/2. 1/2 times 2 is 1, so we get minus 1, which is what we need here, and then e minus t is already there. So all we have to do is multiply this by a t such that when the powers add up, we get 1/2, and all we need is t to power 1. So this is good enough. So then, and rewriting this in a more compact form, we can say dy dt is really 1 minus 2, because these two terms have negative power, so we can put them in the denominator. So we end up with 1 minus 2t, which is that expression divided by 2 times t to 1/2 power e to the t power. Okay, so now we have to calculate dy dx, right? Let's do that. So also, we have x as 1 over t, therefore we can just say dx dt is simply minus 1 over t squared. I'm pretty confident that you all know how to do this, so I'm not giving so much details about this. Okay. All right, so now we can calculate the slope of the line that we have given in this form, in parametric equation form. So this is just one line given to us in parametric form. Okay, so to do that, all we have to do is divide this expression, which is dy dt, by this expression, which is dx dt. So we have dy dx equals, using our formula, right? That. So we have all of that, all of this, which is 1 minus 2t divided by e to the t. We're dividing that by this, so we're going to get a complex fraction, so let's simplify it quickly. We change the division to multiplication, and then we flip this term. Dx dt will flip it. And so this will be minus, let me write it like this, minus t squared over 1. Okay, we can simplify this right away. So what we will get is just distributing this into that, we will get minus times minus, it's positive, so I'm just going to write it first here, 2t cubed, positive 2t cubed, right? And then multiplying this by 1, we get minus t squared. I swapped this spot because I want that minus, the term with the minus to have that in the middle. Okay, divide that by, so 2t, the same thing, right? 1 times all of that gives us the same thing, like that. Okay, now we can maybe factor this. Let's do that. And we have t squared times 2t minus 1 divided by that, and e to the t. And let's see, so we can combine these two terms, right? T squared and t to 1/2. We can simply subtract this from this power, and we get 2 minus 1/2 is just 1.5, or 3/2. So we have t in the numerator to 3/2 power times 2t minus 1 divided by, all we have left in the denominator would be 2 times e to the t power. Okay. So that expression represents the slope of the tangent to this curve. Okay. And of course, t being, we can then determine that slope for any time variable, for any value of the time t. All right, so let's have a look at another example for case 1, which is determining the slope or the equation of a line that is tangent to parametric a line that has been given to us in terms of its parametric equations. This time the parameter is theta, and we are told that theta is equal to pi over 6. So find an equation of the tangent to the curve at the point corresponding to the given value of the parameter. So first we have to find the slope, which means find dy dt divided by dy dx dt. And then given that pi over 6, we will have to figure out a point, x and y, which we can use in that same formula, point slope formula we learned about many semesters ago, right, in basic algebra. But the first step is just figure out the slope of this parametric equation. All right, so we have, so the slope is, maybe I should put here the solution. You might want to pause the video and solve this on your own and then see how your solution compares with this. Because the concept is really basic, but the notation and the method is just calculus, and it's different than basic algebra. So the slope of the tangent line for these parametric equations would be dy dx, which we can obtain by taking the derivative of this equation with respect to the variable theta divided by dx derivative of x with respect to theta. So given this one, we have cosine cubed theta, then the derivative would be, or dy d theta, the numerator of this expression would be 3 times cosine squared theta times, of course, by the chain rule, that minus sine of theta. Okay, for the expression for x, which is given as sine cubed theta, then dx d theta, or the denominator of this expression, is 3 times sine squared theta, right, times, by the chain rule, the derivative of sine theta, which is cosine theta. Okay, you don't need the parentheses, you can just write cosine theta. Okay, so now, given these two expressions, we can plug into this expression. So we have dy dx is, since we're introducing this, I don't mind rewriting this so you get used to it, to the expression here. And then take this divided by that. I'm going to put the minus in front, minus 3 cosine squared theta sine theta divided by the 3 sine squared theta cosine theta, right? Of course, this 3 and this 3 cancel out, and we end up with, so this we have after, because this cosine theta with one of this will cancel out, and we end up with minus cosine of theta in the numerator, this sine theta, and one of this sine theta, since we have sine squared theta, one of that cancel out with that, so we end up with sine, just the sine theta in the denominator. And what is this? This is cosine theta over sine theta is just cotangent theta, so we end up with minus cotangent theta. Okay, so this is the slope of this parametric equation that has been given to us in terms of parametric equations, but they want us to find the equation of the tangent to the curve at this point, right? So we're going to have to find out a point on the line at that. So at theta equals pi over 6, what is the value of x and what is the value of y? We need to find that point, okay? Because the tangent line is going through that point. Okay, so let me maybe put here. So thus, at pi over 6, or at theta equal, I should have said at theta equals pi over 6, we have minus of, since this applies to any angle, but we want to know the slope at this particular angle. Okay, so minus cotangent of pi over 6. This is the same thing as minus cosine of pi over 6 divided by sine of pi over 6. And then we have minus cosine of pi over 6 from trigonometry, we remember, and that is square root of 3 over 2. And sine of pi over 6, again from trigonometry, we remember it's 1/2. So this is just a complex fraction. 2's cancel out. We end up with minus square root of 3. So that's the slope of the parametric equations at theta equals pi over 6. So let's find out the x, the value of the x and the y at that theta value. So we have, and I'll just expand on that. So I'll at theta equals pi over, so all these calculations apply just to that parameter value. Theta equals pi over 6. So we have x, here's the expression for x, sine cubed theta. So we have sine cubed pi over 6. We know that sine pi over 6 is just 1/2, 1/2 cubed, right? So we have 1/2 cubed, and then of course this is 1 over 8. So at theta equals pi over 6, we also need to calculate a y value. The parametric equation for y was this, cosine cubed theta. So we have cosine cubed at pi over 6. We know that cosine of pi over 6 is square root of 3 over 2. So we have square root of 3 over 2 cubed, like that. Simplifying or distributing this power into this, we will get 3 square root of 3 over 2 cubed, which is 8. So we have the slope of the tangent line, which is that. Now we have a point, right? We have the x and y values. So we have 1 over 8, comma, 3 square root of 3 over 8 as a point. Now we can use the basic formula, the point slope formula actually, from basic algebra. So using this formula, I'm sure you quickly remember this, right? This one. Using that, we can find the equation of the tangent to this parametric equation. So we have y is y minus y1. I'm going to plug in what we found for y as y1. So y minus 3 square root of 3 over 8 equals m, which at pi over 6 was negative square root of 3, times x minus x1, which is 1 over 8. Okay, the rest is just simplifying this. So we have y minus 3 square root of 3 over 8 equals, distributing this minus square root of 3, we have minus square root of 3x plus square root of 3 over 8. Okay, so we're going to move this to the other side and add it to square root of 3 over 8. So y equals minus square root of 3x plus square root of 3 over 8. Moving this minus becomes positive. And of course, these two we can combine, right? So let's do that. And we get, y equals minus square root of 3x plus 4 square root of 3 over 8, which then simplifies to just square root of 3 over 2 after we combine and simplify it. Okay, so here we have the equation of the tangent line to a case where the information was given to us in terms of parametric equations. Okay. So let's see another example. Now this one takes us through another topic that we talked about in Calculus 1, which was when a curve is concave up or down, right? So when the second derivative is positive, it's concave up. When the second derivative is negative, it's concave down. So this is one case where we have to apply that formula that I talked about. See that on the first page here, when I mentioned that to find the second derivative for a set of parametric equations, all we have to do is replace that y with dy dx, with the first derivative, that is. And then that will, and then find the derivative of that, the first derivative in the numerator, divided by the same thing as the dy dx. Okay, so the denominator doesn't change, but the numerator, we're just going to take the derivative of the first derivative. Okay, so this is where we can apply that. So go ahead, pause the video. That's what I suggest, because you've seen enough of this technique that you should be able to make substantial progress for at least 90% of the solution here, if not the 100%. But even if not, just give it your own thinking and see what you come up with. Okay, so find dy dx, find the second derivative, and then say for which values of t is the curve concave upward. All right, so again, we start with finding dy dx, which is the derivative of y with respect to t divided by derivative of x with respect to t. And I should remember to put dt. Okay, like that. And so in this case, we can just go ahead and directly obtain these derivatives. So for dy dt, we have minus sine of t, right, as the derivative of that, dy dt. So we have minus sine of t divided by dx dt, then it is again minus sine of 2t, right? And then by the chain rule, we have to take the derivative of 2t, which is 2. So I'm just going to put that 2 here in front. So minus 2 sine 2t, derivative of that. Of course, this simplifies to positive, right? So this is sine of t divided by 2 sine 2t. So now recall in trigonometry, we have an expression for sine 2t, for the double angle, sine double angle, right? It's 2 sine t cosine t. So let's recall that. Recall that sine 2t is equal to 2 sine t cosine of t. So we can replace for that with this expression. Let's do that. So we have dy dx equals, so I'm going to start with this again. So sine t over 2 sine 2t. Now I'm going to replace this piece with that. So sine of t divided by 2 times all of that, 2 sine t cosine of t. So this sine t and this sine t cancel out. We get 1 over 4 cosine of t. Of course, we know that the reciprocal, we have 1 over 4 times 1 over cosine t, right? That's that expression. But 1 over cosine t, or reciprocal of cosine function, is the secant function. So we can also rewrite this as 1 over 4 times secant of t. And this is the dy dx. This is the expression for the slope. Okay, so this is, they wanted us to find dy dx. This is it. So we've answered part of this question. Now we have to answer this question, the second derivative. So just like that formula on the front page, now d squared y dx squared is equal to, so I'm just going to write the formula, d dt. I'm going to insert dy dx. So dy dx divided by dx dt. Dx dt. Okay. Okay, so the derivative of the derivative, or the second derivative of this expression, the second derivative of that, but the derivative of that should go here, right? Dy dx, we're just taking the derivative of that expression again with respect to t. Derivative of secant t is equal to secant t tangent t times tangent of t. So let's write that. I'm just gonna, well, let me write that here. 1/4 secant t tangent of t. So I just wanted to put the parentheses so that t and this t doesn't mix up. And then that all divided by dx dt. Now, when you divide this, in this expression, when you divide by dx dt, you shouldn't divide by the simplified version. Notice that if you grab dx dt from here, it's that minus was simplified. This is simplified after this. So you don't want to grab the simplified dx dt because the numerator here is different than that. So you want to get the original dx dt before you simplified it to that extent. So I'm not going to write 2 sine 2t, 2t. I'm going to write minus 2 times sine 2t because that's the original expression for dx dt. And that's what we need here. So minus 2 times sine of 2t. Okay. And so this is, once again, we can apply this expression, since sine 2t is 2 times sine t cosine t, right? So I can replace that with this. So let me do that again. So we have 1 over 4 times secant t tangent t, and then minus 2 times 2 sine t cosine t, right? And let me put the simplified version here. So we have, well, I don't want to simplify all of it in one step, so let me just do partial simplification. So we have 1/4 secant t tangent t divided by minus 4, right? 2 times minus 2. Minus 4 sine t cosine of t. Okay. All right. So we can still simplify this because we still have a complex fraction, and there's a bunch of other things we can simplify actually. If we rewrite secant t in terms of 1 over cosine t and rewrite tangent of t in terms of sine t divided by cosine t. So let's do that. So we have, I'm just going to say, so for that we have minus secant of t times tangent of t divided by 16, right? 4 times minus 4, 16 sine of t times cosine of t. So let's expand secant t to 1 over cosine t and tangent t to sine of t divided by cosine of t. And I'll do that here, just so I have enough room here to write something else. Hopefully I can fit all the solution on this one page. Okay, from that we have minus, that's that minus, and then we have 1 over, instead of secant of t, I'm going to put 1 over cosine of t times, instead of tangent of t, I'm going to write sine of t divided by cosine of t. All of that divided by, of course, 16 sine of t and then cosine of t. Okay, so now simplifying things, we have, we can write sine of t in the numerator, sine of t divided by cosine squared t. So we can write minus sine of t divided by cosine squared t, this times that, and then all of that divided by 16 times all of this. Okay, so this complex fraction, we can simplify it again, so we end up with multiplying cosine squared t by this, we get cosine cubed t in the denominator. So we have, let's see, so we have minus sine t, and sine t, by the way, also cancel out. So, but let me do it in steps. So sine of t divided by 16 sine of t times cosine cubed t, right? This cosine multiplying by that. I'm just simplifying this complex fraction with 1 being the denominator of this one. Okay, so that and that this cancel out, we will end up with, and maybe I can write one more line before I write on the right hand side. So we have d squared y, or the second derivative of the slope with respect to t, is minus 1 divided by 16 times cosine cubed t. Oops. Like that. Okay. And so, but again, cosine 1 over cosine cubed t, we can rewrite it as, because this is reciprocal of cosine t, so we can write it as secant cubed t. So we can, well, let me box this. So either that, either this, so this is correct and done, or we can write it in terms of secant d squared y over dx squared equals minus 1 over 16 times secant cubed t. Either that or that. Okay. And then they also ask us to, one of the last things they asked is, for which values of t is the curve concave upward? Okay. So the curve is going to be, because we already have a negative here. So if this quantity is negative, negative times negative, we get positive, which means the second derivative is positive, which means the curve is concaved up. So if this piece is negative, we're going to get a positive second derivative, taking into account this minus 2. So this has to be negative. Okay, so let me write that here. I think I have a little bit of space left here. So we can add this. So the curve is concaved up when this term, or secant cubed t, is less than 0. Okay. So if that is, that's just reciprocal of cosine t. So if that is, let's see, so if that's, so when this happens, if you remember the, well, let's remember this, the unit circle from trigonometry. Where was the cosine? Because this is just a reciprocal of cosine function, right? Secant is. And we know, we remember that remember we're operating in this range for t. So t varies, can only vary between 0 and pi. So within this range, where would cosine be negative? Well, recalling from the, I'm just going to draw a tiny little circle here from just referring back to trigonometry. Right? If we have a unit circle here, and t is ranging from 0 to pi. This is the range where t is allowed to vary for this problem. 0 and pi. Now within this range, cosine is negative in the second quadrant here. So if we have t thus t must vary between pi over 2 and pi for this quantity to be negative. Pi over t to pi. Okay, so that's the last thing they asked us to identify. For which values of t we have concave upward along the curve, and that's when. Okay, so this is where cosine is negative, right there. On that side is positive, and this is right there is pi over 2. So from pi over 2 to pi, we're going to have that expression negative, which means this whole thing will be positive. Okay, so let's look at another example. Here, we're asked to find the points on the curve where the tangent is horizontal or vertical. So this goes back to that on the first page when we said when dy dt is equal to 0, we have a horizontal tangent. Sorry, I think the page was crooked, so I apologize for that. So this should be. And if the dx dt is equal to 0, then we have vertical tangent. So we will look at, first we have to calculate dy dt, and then dx dt, and then we will look at where these quantities are equal to 0. That's going to tell us where we have a horizontal tangent and where we have a vertical tangent. So first of all, notice that since they leave open, there is no, here our parameter is theta, but there is no limit given to us. We're not told from between which limits theta is going to vary. So we're going to assume that it's going to vary over the whole range from 0 to 2 pi. Okay, so let's make a note of that. Entire curve. Over theta being from 0 to 2 pi. Okay. So within this, then let's find where we have, within this interval, let's figure out where we have a horizontal and where we have a vertical tangent. So when dy d theta is equal to 0. Okay, so given the fact that we have y, that is our expression for y. So therefore, dy d theta, it's going to be equal to, by the chain rule, we have e cosine theta, but then that multiplied by minus sine theta. So minus sine theta times e to cosine theta power. Okay. So then, based on this dy d theta, thus dy d theta here is equal to when, because this part is never 0, right? This part. So this quantity is 0 only when sine theta is equal to 0. And within this range, when is that going to happen? That happens at theta equals 0, and it happens again at theta equals pi. So when theta equals 0 and theta equals pi. Okay, like that. So that's when we have horizontal tangent. Well, let's see. And then, so that's the theta value for which we have a horizontal tangent. But they're asking us to find the points. So we still have to find the points at these two theta values. So at theta equals 0, we need to find what is the x, what is the y. At theta equals pi, we need to find what is x, what is y. Because that's what they want. Find the points on the curve. So we will do that next. I will do a little table here, and this being so theta, and then we have x equals e. I'll just rewrite it since it's off the screen, and then y equals e to cosine theta. Okay, so we have that, we have that. We know those two values are what we're looking for. So theta equals 0 and theta equals pi. So let's find the x and y values for each of these theta values. Okay, so we have e to sine theta being 0, it's just 0, e to the 0 is 1. So we have 1. Y value, cosine of 0 is 1, e to the 1 power is just e. And then for theta equals pi, sine of pi is 0, e to the 0 power is again 1. And then e to cosine of pi is minus 1. So this y would be e to the negative 1 power, or equals 1 over e, right, when we write it in positive power. So it's these points where we have the horizontal tangent. Let's make a note of that. Are at 1 comma e and 1 comma 1 over e. We have to do the same thing and find the points at which we have along that curve, along this curve, such that the tangent is vertical. So let's do that. So vertical tangents. Now we will look at, let me bring this back. Vertical tangents occur when dx dt is equal to 0. Okay, so let's find dx dt. We have cosine of theta, e times e to sine theta. Okay, this of course by the chain rule. Okay, so then let's see for which values of theta this quantity is 0. So dx dt is 0 only when, because this quantity is never going to be 0. But this quantity can be 0, so is 0 when cosine of theta is equal to 0, right? That's the only case when dx dt is 0. Well, within this range of theta, within these this interval for theta, what theta values would make cosine of theta equal to 0, where we have pi over 2, and the other one is 3 pi over 2, right? So theta equals pi over 2, and theta equals 3 pi over 2. Okay, so just like before, let's make a table here, but this time instead of 0 and pi, we will have theta, pi over 2, and 3 pi over 2. Okay. So once again, so we have x and then y sine of theta. So we have pi over 2 and 3 pi over 2. And so when theta is pi over 2, sine of pi over 2 is 1, e to the 1, or e. When cosine of pi over 2 is 0, so e to the 0 is 1. And then sine of 3 pi over 2 is negative 1. So e to negative 1 is just equal to 1 over e. And cosine of 3 pi over 2 is 0. E to the 0 power is 1. Okay, so we can then write the points for the vertical tangent. Are at e comma 1, right? That's x, that's y. And 1 over e comma 1. Like that. Okay, so let us do another example. And then we will go to case 2, which is calculating area of equations that have been given to us in terms of a third parameter. Okay, we will do that after this. This would be a last example about applying calculus to finding equations and finding tangent lines. Okay, so here they're asking us to find equations of the tangents to the curve that pass through this point. So we're going to have to find dy dx. We know how to do that. It's dy dt divided by dx dt. And then we're going to have to use that point slope formula to find a tangent line, given the fact that the tangent line is going through that point. So we've done this in basic algebra, but we have to do it for parametric equations, and that requires calculus methods, right? So now you know why we didn't study these back then, because we didn't have access to derivatives. We didn't know how to calculate derivatives at that time. Okay, so the first thing is calculate the slope. Let's do that. You might want to pause actually and maybe work on this for 20 minutes and then come back to the video. And hopefully our answers agree. So given this equation, x equals 3t squared plus 1, then dx dt is simply 6t. And then given that y, parametric equation for y, then we have 6t squared, right? 6t squared. And then, so we have dy dx, or the slope is given in terms of dy dt divided by dx dt. Dy dt, oh, wait, well, I forgot to write dy dt here, sorry. So dy dt is this term, or this expression, 6t squared, divided by dx dt, which is 6t. So this expression simplifies to just t, right? And this is the slope of the tangent line. Okay. So now, so recall, we've used this already once. We're going to do it again. Recall y minus y1 equals m times x minus x1, right? From basic algebra. So we have, in this case, y is y. Instead of y1, let's put all of this. So we have y minus 2t cubed plus 1 equals m, which is t, times x minus x1. And let's take this for x1. 3t, so 3t squared plus 1. Okay, like that. So let's call this, because this is an important equation, we will refer back to it again. Let's call this equation 1. Okay. Like that. So now we are told that this tangent line, we know the slope of the tangent line, t, and we used the entire y equation for our y1 and the entire x equation for x1, but we are told that this has to go through this point, 4, 3. So we will then replace y and x with those two values. And so we will replace y with 3. We will replace this x with 4. Okay, to make sure that this line, it's going to go through that point. And I'll write it down here too. So if pass through 4, 3, then let's replace that with 3 minus what we had. Instead of, well, t is t, but instead of x, we have 4. Like that. Okay. Now the rest is just simplifying, distributing and simplifying things. So I'm just going to start from here. So 3 minus 2t cubed minus 1 equals t times 4 minus, I'm going to distribute this, minus 1. Then we have 2 minus 2t cubed equals, so we have let's see, so that's 3 minus 1 is 2, that, and then we have, 4 minus 1 is 3, so we have 3 minus 3t squared. Okay, so let's distribute the t into that. 3t minus 3t cubed and then so let's see, so if we move everything to one side, so 2 minus 2t cubed minus 3t plus 3t cubed equals 0. Okay, if we simplify, we can simplify these two, right? So we have 3t cubed minus 2t cubed, we have t cubed, and then minus 3t plus 2 equals 0. Okay, so we're going to have to find the t values for which this equation is valid. So let's see. So we have, well, note that we learned how to find the rational zeros of a polynomial, right, in basic algebra or pre-calculus 1 classes. So based on that, but this is a small expression, so we can just randomly try some numbers that we think might work, one of them being t equals 1. It just happens that if you try t equals 1 in this equation, it'll be equal to 0. So it turns out that positive 1 is a rational 0. So let me make a note of that here. Note that t equals 1 is a 0 of this polynomial. Okay, and it's just a random good guess, first guess, I guess. Polynomial. And so by long division, we can find factors of this, is what I'm saying. So by long division, we have, maybe I can fit the long division right underneath this. So like that. So we have t cubed minus 3t plus 2 divided by t minus 1, right? T minus 1. Because t equals 1 means t minus 1. And we're supposed to end up with a 0 remainder for this, because if you plug in 1, you get 0. So that means this is a good thing for us. We're going to find factors of this expression. Okay, so then we end up with using t squared here. T squared times that. We have t cubed minus t squared. And then subtracting these expressions. So we end up with 0 t cubed and minus t cubed. These two end up with equaling 0. And then we end up with minus t squared. We end up with t squared minus 3t plus 2. And then we have to get t squared from this, all we have to do is add plus t there and then distribute it to both terms, which means we get t squared minus t, and then subtract this from the expression above it. Once again, t squared minus t squared, we get 0. And then minus 3t minus minus t will be positive t. So add that to minus 3t, we get minus 2t plus 2, of course. Right? There's no constant to subtract from that, so we just write it down. So to get minus 2t from this, all we have to do is add a minus 2 up here. And then we end up with minus 2 times t is minus 2t, minus 2 times minus 1 plus 2. Subtract this from the expression above it, and we end up with 0, just 0. So this is 0, right? Minus 2t minus minus 2t. 2 minus 2 is 0 again. So what we found is that this expression can then be factored into t minus 1 times all of this. So let's write that here. I think, let me write it on this page since I have a little bit of a space left, and then I'll go to the next page. But I want to write that over here, right next to it. So we have t cubed minus 3t plus 2 equals 0 can be written as t minus 1 times all of that, t squared plus t minus 2 equals 0, right? But we can factor this quadratic equation easily, so let's do that. T minus 1 times t, oops. So we have t and t here, and then plus 2 and minus 1 here, right? So then we have t minus 1, so we can combine these two. T minus 1 squared times t plus 2 equals 0. So we have t equal, from this we have t equals 1 as one value for t, and then the other one, t being t equals minus 2. Okay, so these two values. So let me move to the next page. Okay, so now we're going to revert back to equation 1, right? Because this equation gives us the tangent line, but we're going to have tangent line at, it looks like, at 2 locations, at 2t given to us with the t. Since this is the slope of the tangent line, and we found 2t values for which we're going to have tangent. Okay, so let's plug in for t with each of those values that we found to find the equation of the tangent line, which is what they ask us. Okay, so this is so parameter values t equals 1 and t equals negative 2 and equation 1 Okay, so let's do that. So I'll just rewrite equation 1. Y minus 2t cubed plus 1 equals t times x minus 3t squared plus 1. Okay, so when t equals 1, and x equals 3t squared plus 1, y equals 2t cubed plus 1. Right, this is our equation 1, by the way. So we have, I'm just going to plug in for t with 1, right? So we get 1 cubed is 1 times 2 is 2 plus 1 is 3, so we get y minus 3 on this side. Here we get 1, right? 1 times all of this, and then we have, so we have 1 times x minus 1 squared is 1 times 3 is 3 plus 1 is 4. So x minus 4. So what do we get? We get y minus 3 equals x minus 4. Therefore, y equals, move this to the other side, we get x minus 1. So this is the tangent line at 4, 3. So let's see what passed through the point. So that's one of the tangent lines. Tangent line when the parameter t equals 1. Okay. And this tangent line does go through that point 4, 3. So we know that. That's part of this equation. Okay, let's see. Well, that's part of the t values that we found. So we already guaranteed with that. These t values guarantee that the tangent line does go through 4, 3. Okay, so then for t equals negative 2, let's do the calculation again. So when t equals negative 2 and x equals 3t squared plus 1, y equals 2t cubed plus 1. Again, we're going to calculate this equation for when t this time equals negative 2. So we have like that. So maybe I should highlight that. So this is our equation. Okay. So we have y minus 2 cubed is minus 8 times 2 is minus 16. And then minus 16 plus 1, of course, right? Like that. And then this t is going to be minus 2 times x minus t squared is positive 4 times 3 is 12 plus 1. Okay. So now we're going to simplify this. We have y minus 15 equals minus 2 times x minus 13 there. Okay, so then we have y plus 15 minus 2x plus 26 and then move this positive 15 to the other side, y equals minus 2x plus 11, right, after combining this with that. So 26 minus 15 gives us 11. Okay, so this is another second tangent line, or tangent line at when t equals so tangent line when t equals minus 2. So if we calculate each of these equations, by the way, so when t equals, this parameter equals minus 2, what do we get for that? Notice that if we substitute t equals 1 in each of these, what do we get for x? We get 3 plus 1, 4, and we get 3 here. So the point 4 comma 3, which we were given at the beginning, one of the tangent lines, that tangent line, when t equals 1, passes through this point. So apparently with this, we have another tangent line that goes through this point, because if you substitute for x, or t, sorry, for t with negative 2, you get, what do we get? We get positive 4 times 3, 12 plus 13, x equals 13. So let's add that here. So this is the tangent line at, so x equals, so 3 times minus 2 squared plus 1, that's 13. Y equals 2 times minus 2 cubed plus 1. So this is minus 8 times 2 is minus 16 plus 1, minus 15. So these two, so tangent line when t equals minus 2 at this x value and this y value. Like that. All right. So now this was all case 1. When we apply calculus methods to parametric equations, if we were interested in finding the slope of the tangent line and the equation of the tangent line. Case 2 is when we're interested in finding the area under a curve for which we have the information in terms of parametric equations, right? So calculating the area, this is being case 2, under a curve defined by parametric equations such as this. Okay, and this is some interval of integration for t, which we will look at next in the upcoming formulas. So the area, generally, when we learned about how to apply calculus methods to finding area, this is what we learned, right? If we want to calculate, first of all, we need to have a definite integral like this, and if we're integrating with respect to x, then this would be our integral. Area equals the equation dx from these between these two limits. So this is just generally when we first introduced integrals as a means to calculating area. But this applies not to situations where we have parametric equations. Okay, so how does this change? How does this integration formula change for parametric equations? Well, we're going to replace this y. Oops, sorry. I was off the screen. So for this y, we will replace this y with its parametric equation equivalent, right? Because we know y equals gt, g as a function of t, right? So in this integral, we will replace y with g as a function of t. In other words, we will replace it with its equivalent parametric equation. And we will replace dx with f prime t dt, which is the derivative of what x is equal to in terms of a parametric equation. For y, we replace it with g of t without any change. For dx, we will replace it by the derivative of this parametric equation that represents x, like that, in terms of the third variable t, or sometimes maybe theta. Then what we have is this formula, right? So gt, g of t, replaced y, right? Maybe I should, can I fit both on? Yes, you can see them on the screen. G of t, g as a function of t, replaced y, and dx was replaced with f prime t dt. Okay, like that. So this paragraph is just explaining how the replacement, how this was adapted to parametric equations. That's all. Calculating area for parametric equations. But I've listed two formulas just as a addition here to what your book explains. So we will use this when dt replaces dx. So when integration happens with respect to the x variable, then this is the formula that we use. But when the integration happens with respect to the y variable, then what we do is the opposite. We will take this equation that represents x. In other words, so replaces, well, you can see it here. So this is replacing that when integration is along on the x variable. But notice that here we're integrating with respect to the y variable. So ft replaces x. We can do that because x is equal to f of t, right? So f of t replaces x, and then we take the derivative of the function that represents y with respect to t. We take the derivative of that, and that function, that derivative dt, replaces dy. So we have to be careful which case are we doing. Are we integrating with respect to x, or are we integrating with respect to the y variable? That's going to impact which function gets its derivative placed inside the integral. Okay? All right. So if we're integrating with respect to the y variable, it's the function that represents y that has to have a derivative inside the integral. Okay? Again, you don't really have to memorize these, or you wanna know how to use them. That's all. Okay. So let's look at an example of applying this method to calculation of area for a line for which we have parametric equations. Okay, so here it says find the area enclosed by this curve given to us in this parametric form and the y-axis. Okay, so this curve plots, and I will draw an example of it. You can do this manually, by the way. You can get a feel for what this curve looks like, either manually or using a graphing tool, a technology tool such as Desmos on the internet, which is free. So if you go to desmoscalculator.com, you should be able to plot this, and I will use, so in Desmos, once you go to that website, all you have to do is enter it as this. So instead of x, so you will be entering it just like this. You would enter parentheses on Desmos, calculator. You would enter, instead of x, you would say t squared minus 2t, comma, for y, you would enter square root of t. And then as soon as you do this, beneath it, it'll open a window where it says enter the interval over which you want to plot this parametric curve for t. So you need to give it an interval for t. So it's going to ask you for that. And in this case, we have to calculate that. We haven't done that yet. But once we calculate those limits for t, you will enter them here and here. And then as soon as you do that, a graph of this parametric equation is going to pop up. It does a very nice job too, this Desmos does. Okay, so but I'm going to show you also here how to do it manually. So the first thing we need to do is this. If you're integrating with respect to the x or y variable, in either case, you're going to need to know where this curve intersects those axes. So they're saying find the area between this curve and the y-axis. So I'm just going to look for any points of t along the y-axis. So we need to know where the curve here intersects the y-axis, since that's what they're telling us. And so that is when x equals 0, right? Or the y-intercept. Okay, so because that's happened, the curve intersects the y-axis when x equals 0. So based on that, we can make use of this equation, right? So 0 equals t squared minus 2t, right? X is 0, has to be, because we're looking for where this curve intersects the y-axis. And then then based on this, let's factor this. That. And so we will have 1t that would be equal to 0, and 1t which is equal to 2. Right? So now we know for which values of t the curve intersects the y-axis. So I will plot this because I think it's helpful. In this particular example, it's really helpful if we have a graph of this parametric equation drawn first. So okay, so I'm going to So with Desmos, like I explained, you can do it very quickly in a matter of seconds. And also manually, if you prefer, you can do that here as well. So this is what we would do. So we have the variable t here, and then the x, and the value of y. So I used some, because t has to range, or when the curve intersects the y-axis, it happens at these two values of t. So, but I'm just going to use other values of t, including these two, to just get an idea of what the graph looks like, knowing that at these 2 points, my curve is going to cross the y-axis, because x will be equal to 0 at those points. Okay. So I will use these, t equals 0, I will pick some easy numbers, 0.25, 0.5, 1, 1.25, 1.5, and instead of 1.75, let me just jump to 2. Okay, I think that's enough values for us to plot this graph. And then, so for when t equals, can I put this on the screen? Well, I'm going to write them here again. So x equals t squared minus 2t, and then y equals t. So I've already calculated some values. I'm going to write them here, but please verify me on these. So that, and then for t equals 0.25, I got minus 0.4375, 0.5. When t equals 0.5, we have x equals minus 0.75, and y is going to be that. When t equals 1, we have x equaling minus 1, and y equaling 1. And when t equals 1.25, we have x equaling minus 0.9375, and of course y would be equal to 1.11. For this t value, x is this, and y is 1.22, and for t equals 2, x is going to be equal to 0, and y is going to be equal to square root of 2. And I will need my ruler here. Okay, so let's draw that. Like that, and then looking at these values, then we have, I want to give most of this blank space to the negative side of the x-axis. So then we have like that. And then a graph of these points. I'm just going to draw a rough graph based on what I saw on Desmos site. So if we have, if this is 1, let's say, if that's 1, and let's say if that's -1. Right, so at x equals -1, y equals 1. So we know at least that. But the curve does something like this. So, well, I'm going to draw a dashed line just to make sure that my graph is, as much as I can draw it, is to scale. So, well, my line should be straight on top and like that, roughly speaking. And so the graph does something like this. Something like that. And then I can basically lightly shade it here. So this is the region we're talking about, or the problem is asking about. What is the area of this region? And this is where we have 0, when x is 0, which is here, y is the square root of 2. So that's that point. That's one of the points, 0 comma square root of 2. That's that point. And 0 comma 0 is, of course, here. Okay, and they're saying find the area enclosed by the curve and the y-axis. So we're calculating this region. Okay, like that. Okay, so now that we have that, so let us begin. So we're integrating with respect to the y-axis. So if I bring this, maybe I can put that here. We're going to apply, we're applying this formula, this one, where x equals f of t is going to be plugged into the integral as it is. And the y values will be from 0 to square root of 2. But when we switch to t, then we have to change those intervals, right? We know that the t, for t varies from 0 to 2. Okay, but with respect to the y-axis, the integration is happening from y equals 0 to y equals the square root of 2. As a matter of fact, let me write that here. So this point is associated with parameter value 2, and this point is associated with parameter t value equals 0. Okay. And we're going to use this one. We're integrating with respect to the y variable. Okay, so let me write down the area formula for this. Looking at that, we have area equals, I'm just going to start with dy, and then I'm going to transition to dt. So my limits of integration first will be 0 to square root of 2. So y equals 0 to y equals the square root of 2. And then for x, we had, for x, what did we have? Well, let me write it as it is. So I'm just going to write x in terms of t. First, I'll write this out generally, and then I'll narrow it down to more specifics. And then dy, right? That's what we want. That's our formula. And then, so we have, so this will be equal to, like that. So that'll be equal to y from 0 to square root of 2. Now this function has to be the larger value minus the smaller value, right? So if you look at this graph, all of this graph, the y value here along this line, x value, which is 0 along this line, it's going to be higher than any place on the curve because all these values are negative. Right there, you can still see it on the screen. Right? They're either 0 between t equals 0 and t equals 2, the x values are either 0 or negative. So the highest value of x occurs on the y-axis. So to end up with a positive value for the area that we're calculating, we have to subtract the smaller values from the larger value. So if you do, you can still get the same answer at the end, the same value, but it's going to be negative if you subtract this from that. It won't, you'll end up with a negative area value. To end up with a positive area value, we must make sure that all the x values that we're subtracting is the larger minus the smaller one. If you do smaller minus the larger one, then if you do these x values minus that, then you will get a negative area value. So to ensure that we end up with a positive area value, then we have this, so the x on the right, x values on the right, minus x values on the left. In this case, because the x values on the left happen to be smaller. If this curve was on this side, then we would say these x values will be, x values will be larger than this corner. So you would say this curve minus this line. But here we have to say this line minus that in order to make sure that we get a positive area value. So that means I'm going to write x sub r, or x values on the right minus x values on the left. Okay. So and this would be dy still, because the limits of integration are from 0 to square root of 2. It's from 0 to a square root of 2. When I switch this to dt, the limits of integration will go from t equals 0 to 2. Just keep track of that. Okay. And I will, let me actually make a note of this on the graph, that this line, where would I, so this line represents x on the right, and this line represents x values on the left. That's for this piece of the integral. So for this line, for x sub r, all x values are 0, right? So let's switch to t variable. So this will be, I'll just write it here. Well, maybe I can write it underneath this. I have enough space still. So a equals, notice I'm switching from y to t, which goes from 0 to 2. 0 and from 0 to 2 for the same points. Okay. And then x of r, that'll be 0, right? X value on that line, y-axis, is going to be 0. So we will have 0 minus the x values on this curve. So they will be x as a function of t, and then of course dy. So what will replace dy? Let's look back at our formula. dy is replaced by g prime t dt. So we have to take the derivative of the parameter equation for y dt. So let me write it down. So since it was given as y, not gt, so I'm just going to say y prime t dt. Okay, so that's how that transition happens. All I was explaining here is that if you don't do this, or if you don't care and you get the order wrong, you end up with a negative area value. That's all. In which case you say, hey, this is the area I'm calculating, so you just write it as a positive. That's the only. This guarantees that we end up with a positive value. Okay. So let's move to the next page here. Okay. So now we will plug in for these with what we should have. And before that, I'm going to write my equations here, the parametric equations, so we have them on the screen. So given x equals t squared minus 2t and y equals a square root of t, or basically this is t to 1/2 power, right? Given that, we're going to plug in here with what we should. Okay, use these notations as our guide. So we have a equals t from 0 to t equals 2. 0 is just 0, minus x of t, x as a function of t, so it's that whole thing, 0 minus that whole thing, so it's minus 2t, I guess, well, t squared minus 2t. Okay, yeah. And then now y prime would be the derivative of y, right? Y is equal to that. So y prime would be equal to 1/2 times t to minus 1/2 power, right? So then let's plug that y prime, that's y prime t actually. It's the same thing. Derivative of y with respect to t, which is what we did here. So this quantity gets plugged in here for that. Okay, 1/2 times t to negative 1/2 power, and of course dt. Okay, we don't need that one anymore. All right, so now time to simplify this expression and find the integral of it. So we have from 0 to 2, this minus, let's not keep it dangling in front here, let's distribute it. And if we do, we get positive 2t minus t squared times all of that. And of course, we can simplify that too, right? Easily, we can distribute things. If we do distribute this into that, what do we get? We get integral from 0 to 2. And so we get 1/2 times 2 is just 1. T to power 1, the powers add up because the base is the same. So 1 minus 1/2 is just 1/2. T to 1/2 power. Then this times that, we get minus 1/2, of course. And then 2 minus 1/2 is just going to be 3/2. Oops. T to 3/2 power. dt. Okay. And this is a really easy expression to integrate. So let's do that. We have add 1 to this power, we get 3/2, divide by the new power, we get 2/3 times t to 3/2 power. Then this one, add 1 to that power, we get 5/2, divide by the new power, multiply by minus 1/2, So minus 1/2 times 2 over 5, we get minus 1 over 5 times t to 5/2. And then, of course, the limits of integration. So we know for this piece, both of these terms drop out, right? So the only value we're going to, non-zero value we're going to get is by plugging for t with 2. So let's do that. We will have 2/3 times 2 to 3/2 power minus 1 over 5. Well, let me put this in parentheses too. Times 2 to 5/2 power minus 0, of course. This 0 is we get when we plug 0 for t here. Okay. So now we have, what do we get? So this is the numbers I have. After, you can use your calculator, of course, to do this and verify these numbers. But a equals 4/3 times square root of 2, and then minus 4/5 square root of 2. And then, of course, we can add these since they're both something times square root of 2. So a would be common denominator 15. We have 20 square root of 2 minus 12 square root of 2, like that. So we get 8 square root of 2 over 15. Like that. Okay, so this is the case 2 where we apply this method to calculation of the area for curves for which we have information in terms of a pair of parametric equations. Okay. Let's do another example. I know these examples are extensive, but it's okay because they require us to recall many things that we may have forgotten. So it's a good way to refresh our memory too about these topics. So here in the next example of finding the area given a pair of parametric equations, we want to find the area enclosed by the asteroid given to us as that. So let's draw an asteroid to get a feel for, like I say, none of these problems ask us to graph anything, but if you have a graphing calculator or a technology available to you, graph them. Just get a feel for what the graph looks like before you actually calculate the area for it. I'm just going to draw a basic small graph here. Something we can use as a reference, that's all. So we have x and then y. So an asteroid looks like, it's a very symmetric shape or figure. So let me, I will do something. So let's put, so all of these distances must be equal. I'll do my best to make that happen. And then also here, something here. So these constants in front that you see, that's that value A. It's going to be here. It's going to be here. And of course on this side it'll be negative, but it'll be still here on this side. So minus A and then minus A but that's the distance from the origin. That's what that number represents in front. And then we have cosine cube theta and then sine cube theta. So what the shape that gives us is basically something looking like this. So again, all of this, even though my drawing is not going to be that symmetric, even though I'm trying, the correct graph should be very symmetric. And then also connecting these two like that. So why do we call, so this is called asteroid, and the way it is generated is by, if we envision a circle that is around this asteroid. So if I lightly, using dashed line, draw something like that, roughly a circle. Like that. And then imagine a small circle of some radius on the inside, and I will draw that with something like this. So imagine that circle starts here, that the little circle, and rolls along the interior of that larger circle. So this little circle rolls along the interior boundaries of that larger circle, and that point that you see will trace what you see as the asteroid, the red lines. Okay, so maybe if I can find a pencil in my tools here, then I can also add some shading to that drawing. So that would be, I'm just going to lightly shade that. So this is our asteroid. Okay, like that. So we want to find that area given these parametric equations. Okay, so what usually see when anybody calculates this area is they calculate the area in this region and they multiply it by 4 because this shape is so symmetric. So we're going to do the same thing. We're going to calculate this area, which I'm darkening, that area, and then multiply it by 4. Okay, so let me actually say that. So we're going to do that here. So calculate this area and multiply by 4. Because of the symmetric nature of this shape, we can do that. Okay? All right, so let's do that. We will, it really makes no difference in which one of these variables you integrate with respect to, whether x or y, but x seems more natural, so we're going to go with this. We're going to go with this format. So we're going to replace dx. We're going to integrate with respect to x, and then, of course, in this case, we have theta. So d theta is going to replace dx. And because of that, the curve, the parametric equation that represents gt, or the y, it's going to be, well, I'll write it down so we don't have to remember it. Memorization isn't that important. It's how to apply the method that's important. Okay, so let us write down, as I said, we're going to integrate with respect to the x variable. So I'm going to write a equals 0 to a, and I'm going to put a 4 here. Well, I should have this 4, this is what I was mentioning here. So we're going to find this method finds this, so y dx, right? Integral from 0 to a, from here to here, given this curve. It's going to give us this area, but of course we want the whole area, so we're going to multiply it by 4. I should have given myself more room to write that 4, but it's here, and I will make it clear in the next lines. So 4 times that integral with respect to x. Okay, so from here to here, it's just 0 to pi over 2, right? So this is theta equals 0. I'm mentioning this because we're going to switch to theta, right? From dx, we're going to switch to the parameter. So at that point, theta is equal to 0, and at that point, theta is equal to pi over 2. So we're going to have to do this from 0 to 2 pi over 2. Okay? So then let me rewrite this as 4 times. From 0, instead of a, we're going to say pi over 2, and then y with respect to theta, y as a function of theta, d theta. So we switched over from dx to d theta. And because we're integrating with respect to x, y or gt, and then we're going to take the derivative of the other equation, the equation that represents x. We're going to take the derivative of that, d theta. Okay. All right. So the next step, let us. Because we can, again, if you continue with this is based on experience, you're going to get a negative area. So because all these things are symmetric, we can go from pi over 2, we can integrate over x from pi over 2 to 0. So let's do this. So let us use this. Area equals 4 times. I'm going to put pi over 2 here and 0 up there. We're going to start with this, because if we continue with this, we're going to get a negative area. And that's based on experience. Okay? You can try it. You can keep your limits like this and then continue after finishing. You'll see you'll end up with a negative. But let's start with pi over 2 as a lower limit and 0 as the higher upper limit. Y theta d theta. These two are the same thing, but this makes it explicit what the parameter is. That's all. And then so we end up with positive value for the area. With a positive for the area. That's the only reason we're doing this. So now, in order to move the pi over 2 to the upper limit, where it should be, then we have to multiply this integral by minus, right? So a equals minus 4 times 0 to pi over 2 y d theta. I'm just explaining this, but you don't have to do it. And then at the end, when you end up, if you keep this, you will end up with a negative area, and you just make a note that, okay, this is area and it has to be positive. That's all. You can do that too. But this strategy makes sure that we end up with a positive area. So then let's plug in here. Then this will change and become this integral, minus 4 going from 0 to pi over 2, and y as a function of theta times this parametric equation, taking the derivative of this, multiplied by the derivative of this equation. So x prime theta d theta. Okay, so that sets the approach for us, what we need to include in the integral. Okay, so then what will happen, I will start here. So minus 4 times 0 to pi over 2. Since it's off the screen, let me write it here so we can look at them. So x equals a cosine cubed theta, and y equals a times sine cubed theta. Now, given these two parametric equations and this integral, let's see. So y as a function of theta is just that. So we need to include that. Let's do that. So a times sine cubed theta times, now we have to take the derivative of the parametric equation for x with respect to theta, right? So that'll be that. So this will be 3 times a cosine squared theta, and then by the chain rule, the derivative of cosine theta is minus sine theta, right? So let me write minus 3 times a cosine squared theta times the derivative of cosine theta, which is sine theta, which is actually minus sine theta, but the minus is here in front. That's what that is, the derivative of cosine theta. Okay, so then d theta, of course. Okay. So I hope you follow that this is the derivative of that. Okay, let me actually add it here too. X prime theta is equal to minus 3a cosine squared theta sine theta. I know it's a little bit redundant, but hopefully it'll help everyone follow what I'm doing here. All right, then now the next step, we can certainly simplify this, right? We have a minus 4 in front, we have a minus 3 here, and an a here and an a here, and they're like constants, so we can pull them out and put them in front. So we will get, if we do that, we will get a equals positive 12, right? Minus 3 times minus 4. And a times a, we get a squared integral from 0 to pi over 2 of, and then what else we have? We have sine of theta and then cosine theta. So we have, let's see. We have cosine and just cosine theta, cosine squared. Okay, so we have cosine squared, that's the only cosine term, cosine squared theta. Sine theta times sine cubed theta will give us sine to the 4th power theta d theta. D theta, right? Like that. Okay. Now, if we keep these, it's going to be integrating these, it's going to be complicated. But let's recall, we have to make some kind of adjustment here or use some of the identities we know to simplify this. So then recall that sine squared theta is equal to 1 minus cosine 2 theta over 2. Right, we have that. And for cosine squared theta, we have a similar but a little bit different formula. So cosine squared theta is the same thing with the exception of the minus is positive. So equals 1 plus cosine of 2 theta divided by 2. And we can put a parenthesis around that if you like that. Okay, so let's recall those. Because then we can use this to replace the cosine squared theta by something that we can integrate easily. Okay, and then we can then work on that a little more too. Let's do that. So, but because this is sine to the 4th power, so and this is sine squared, so we need to square this again. That's going to cause a little bit more work for us, but nothing we cannot overcome and circumvent and get the final result later. So I'm going to replace each of these with the appropriate terms, including these. So we have, so a equals 12a squared integral from 0 to pi over 2. And then instead of cosine squared theta, I'm going to include that. So 1 plus cosine 2 theta over 2. And that's all I have to do. But for sine to the 4th power theta, I'm going to have to square this because this is just for sine squared, not for sine to the 4th power. So then times 1 minus cosine of 2 theta divided by 2 squared. Okay, and then of course d theta here. All right. Let's see if I have a little more room here. I can add another line. And so let's see what else we can simplify here. We can factor this expression. We can factor 1/2 from this expression. And what can we factor here? This is 1/2 squared, right? Because of this power. 1/2 squared is 1 over 4 times a 1 over 2 factor from here. We get 1 over 8. We can factor this out and then we can end up with something with no fractions inside the integral. That's good. So let's do that. So we will say a equals 1 over 8. Again, this 1 over 8 is 1 over 4 factor from here because 2 squared is 4. 1 over 4. And then 1 over 2 from here. 1 over 2 times 1 over 4 is 1 over 8. Times the 12a squared we had in front from the get-go. 0 to pi over 2. And then all we have left on the inside is 1 plus cosine of 2 theta times 1 minus cosine of 2 theta, squared of course, right? So that power distributes itself to numerator and the denominator alike, d theta. Okay. Maybe I can add another line here, but no, let me go to a new page. It will be too crowded, but like that. But I will go to this, keep it on the screen for a while, like that. So we're going to expand this. This is just binomial squared, so we can easily expand that. Let's do that. And also let's simplify this. So we have a equals 12 over 8 simplifies to 3 over 2 a squared, right? And then integral from 0 to pi over 2. And the first couple of terms, let's keep them as they are. 1 plus cosine of 2 theta. Let's expand that. What do we get? We get 1 minus 2 cosine of 2 theta. And then plus cosine squared 2 theta. And then of course d theta. And that's of course the page number, that's the page number there. That's not part of our equation. Okay. So now let's see, we should distribute all of this, right? Let's do that and do it term by term. So we don't need that page anymore. So let us distribute. So we're going to distribute this 1 into this and then cosine 2 theta into all the 3 terms. So we get, we have 3, this stays 3 halves a squared integral from 0 to pi over 2. And then we have 1 times 1 is just 1. 1 times minus 2 cosine 2 theta. That's itself. 1 times cosine squared 2 theta. Like that. And then now let's distribute cosine of 2 theta into that. So we get plus cosine of 2 theta minus 2 cosine squared 2 theta, right? We're distributing this into that. Minus 2 cosine squared 2 theta, right? And then plus cosine cubed 2 theta. Like that. Let me close the big parentheses, which is here and there. And then, of course, d theta. Okay. So let's see what we can simplify. So we have this term in front stays as it is, 3 half a squared. And then we have, what can we combine? The 1 we cannot combine with anything, so it stays. So I'm just going to say 1 minus. Notice that these two combine, right? These two combine. We don't have any other cosine 2 theta with no power, or power 1. Minus 2 cosine 2 theta, and that positive cosine, they add up to minus cosine 2 theta. So we have that. Then we have a cosine squared 2 theta and minus 2 cosine squared 2 theta. So we have these two that can be combined, right? These two. Minus 2 plus 1, we get minus cosine squared 2 theta. And then finally we have one more term at here, plus cosine cubed 2 theta, close the big parentheses, and of course this is d theta. Now looking at this, these two terms are easy to integrate. But these two, not so much. We have to kind of work with them. This one is easy, right? Because like we mentioned on the previous page though, even though we have to work on it a little bit, it's easy to convert it so it's easier to integrate. That's all we have to do. Keeping in mind that this theta, in this case, is 2 theta. See, we have, this is the formula, original formula, cosine squared theta, which we learned about in trigonometry. But here we have cosine squared 2 theta. What difference would that make? Well, when you switch from this side to that side, or rewrite this in terms of that, 2 theta multiplies by 2 theta, you get or you have 2 times theta. In our case, theta is 2 theta. So 2 times theta in our example will be 4 theta. So it's not 2 theta multiplying by 2 theta. It's 2 multiplying by theta. But in our case, theta is 2 theta. So 2 times 2 theta is going to give us 4 theta. So let me actually do that here. I guess I will write it here on this side. So recall that cosine squared theta is equal to 1 plus cosine of 2 theta divided by 2, right? That's what we just used on the other page. So now we're going to use that to rewrite this so it's easier to integrate. So cosine squared 2 theta, it's going to be equal to 1 plus cosine of 4 theta, right? 2 times theta. In our case, theta is, sorry, let me correct that. So this is the original formula. So I meant to write this like this. Oh, yeah. I apologize for this. I'll clean this up before posting it on Canvas. But that was correct. It should be 2 theta. So cosine, 1 plus cosine of 2 theta. Now, in our case, theta is 2 theta. So 2 times 2 theta, we get 4 theta. And then, of course, divided by 2. So let's keep this in mind. We're going to keep this in mind. We're going to use it later, right? So that we do this to simplify that so we can integrate it easily. Now, how about this one? This one is a little bit more work, but we still can do something to make it easier to integrate. So for this one, so integrating this, let's integrate it separately. In other words, we're going to pull it out, disregard these limits. We're just going to integrate it as an indefinite integral. Okay, and then we're going to put it back in with the rest of these terms because these are much easier to integrate, but not so much this one. So integrating this term separately, so we have this. I'm going to write this in blue so it keeps it separate from everything else we've done so far. So we have, and I'm going to do this as an indefinite integral. So cosine cubed 2 theta d theta. And then we can separate this and write it as a piece that we know it's going to help us, cosine squared 2 theta, and then cosine of 2 theta. So two theta times cosine squared 2 theta d theta. Okay. Now recall that we have a squared identity from trigonometry that says sine squared theta plus cosine squared theta equals 1, right? So that means that thus, so therefore, then if we can say sine squared 2 theta plus cosine squared 2 theta also equals 1. Okay, we're just going to use our theta for that, which is 2 theta. Now, based on this, then we can say that cosine squared 2 theta, which is what we have up here, is equal to 1 minus sine squared 2 theta. Okay? So now, this is okay. So now we're going to plug back in here. Instead of cosine squared 2 theta, we're going to plug back in this term, 1 minus sine squared 2 theta. So then let us do that. After that, we have integral of cosine 2 theta times this 1 minus sine squared 2 theta d theta. Okay, that should do it. Now let us use substitution method here. So after we've made this transition, so let's let u be sine 2 theta. And then therefore, so if that's the case, so then du, it's going to be cosine 2 theta, 2 times cosine 2 theta, 2 times cosine 2 theta d theta. That's d theta, sorry. I need to fix these before posting on Canvas. Okay? So then based on that, we're going to have to replace that d theta. So d theta, it's going to be du divided by 2 cosine 2 theta. Okay? So we found a substitution for here. So we'll have 1 minus u squared. And then d theta will be du over 2 cosine 2 theta. So let's substitute in this integral with what we have. So we have integral of cosine 2 theta times, instead of 1 minus sine squared 2 theta, 1 minus u squared. U squared. Instead of d theta, we put this, du divided by 2 cosine of 2 theta. If you're quick as I know you are, you're going to now say, wait a minute, you're saying du, but you still have theta here. You can't have 2 different parameters here. So, but fortunately, in this case, cosine 2 theta and this cosine 2 theta cancel out. Okay? So because of that, I don't think I have enough room. Maybe one more line here. One more line maybe I can write. So this reduces to integral of 1 minus u squared, right? Du, and of course, let me not forget the 2 here. So 1/2, because it's just a constant, I'm going to put that in front. So 1 over 2 times all of that. It was kind of hidden there. Almost forgot it, but it's there. So 1/2 times 1 minus u squared du. Okay? Now we know how to integrate this, and I'll go to a page, new page. Okay, so now we have let's integrate that. So we have equals 1/2 And this is still, I'm keeping everything as an indefinite integral. There is a reason for that. And then, the reason being that it's just, I'm going to be able to plug it back into the original here. So we will integrate these three terms after transition here. Oops, sorry. Once we're done with this, we can include our result at the end as part of this integral. And we're going to easily integrate these three terms after this transition. That's all. So that's why I kept the limits of integration off. Okay, so we're back here again on this page. So we have u minus 1/3 u cubed, like that. And now let's transition back to theta variable, which was, we took u to be sine of 2 theta, right? So we're going to move back to that. So u equals sine of 2 theta. Therefore, we have 1/2 of sine 2 theta here minus 1/3 sine 2 theta cubed, like that. Or sine cubed 2 theta. Right? So this would be just a 3 here. Let me do that. And I will clean this up. So that 3, just put it here. And I will erase that with a whiteout after the video is complete. Okay, so now we have integrated our most complicated term in the integral, right? And we can, let's see. So we have that. Okay, so we might as well distribute this 1/2 too. Okay, let's not, because we're going to incorporate this in that result. I might as well call it equation 1. So this is our main integral. This one. This one was our main integral. So I might as well call it equation or equation 1 for the area. And then we're going to integrate this into that, or import this into that. And for that, let me distribute the 1/2 as well. So we have 1/2 sine 2 theta minus 1/6 sine cubed 2 theta, and then like that. So we can put it plus c because it was a indefinite integral, but the c will drop out as soon as we incorporate it with the rest of that integral. All right, so now given that, we can insert all of this into that equation we have. So inserting the above result into that, okay, which is that. So what we have here is this term integrated. All we have to do is put the limits of integration for it. Okay, now, or this one. We have that, and we've transitioned from here to here. So now we can put all this back together in a nice and simpler way. So we have a equals 3/2 a squared times integral from 0 to pi over 2, 1 minus cosine 2 theta and then so instead of that, remember that instead of that, do I want to include that? Yeah, I want to, maybe I should do that. So let me, instead of this, so we have these two results. Instead of that, I'm going to put in this expression, 1 plus cosine of 4 theta over 2, instead of all of that. So minus 1 plus cosine of 4 theta over 2. Okay. And then let me close that and say d theta, because the third term, which was that, the third term, this one, we've already integrated. So the result was all of what you still see on the screen. But I'm going to drop the c. Okay, so plus 1/2 sine 2 theta minus 1 over 6 sine cubed 2 theta. Okay. So now I'm going to simplify this term a little bit. So we have a equals 3/2 a times a squared from 0 to pi over 2. And so this we can't do anything about. 1 minus, we can't simplify this anymore. Cosine 2 theta. Now I'm going to distribute this minus, I'm going to separate these two terms. So it's going to be minus 1/2 minus 1/2 cosine of 4 theta. Like that. Okay. And that's d theta plus the rest of this, which is outside of the integral. We've already done that. 1/2 minus 1/6 2 theta, sine cubed 2 theta, that is 2 theta. Okay. All right, so now we can easily integrate all these remaining terms. These we don't bother with. We can just include them. So we have that's 2 theta. Okay, so we have a equals 3/2 a squared. 1, integrate this with respect to theta, is just theta. This one, minus 1/2, right? This must have been sine. So minus stays as it is. So 1/2 sine 2 theta. Minus 1/2 becomes minus 1/2 theta. This term becomes, let's see, so we have minus again because of this 4, so it will be sine 4 theta divided by 4, which would give us 1/8, 1 over 8. 1 over 8 sine 4 theta. And let's add whatever else we have after that. So plus 1/2 sine 2 theta minus 1 over 6 sine cubed 2 theta. Okay, and I still have to include the limits of integration, of course. So close that, and we have 0 to pi over 2, right? 0 to pi over 2. So 0 from 0 to pi over 2. Okay. And then after that, let's see. So now a equals 3/2 a squared. So you know that if we put 0 in these terms, sine 0, sine 0, sine 0, sine 0, minus 1/2 times 0, 0, all of these terms cancel out for 0. So the only non-zero ones that we can find should be when we substitute for theta with pi over 2. So pi over 2 for theta, we get itself. So for sure it's not 0. Now pi over 2 replaced for theta, this 2 times pi over 2, we get sine of pi, which is 0 times minus 1/2. We get 0, minus 0. Minus 1/2 times pi over 2, right? After substituting for theta with pi over 2, we get minus pi over 4. For theta will be 4 times pi over 2. That will be 2 pi after we simplify. Sine of 2 pi is 0 times minus 1 over 8 is minus 0. Sine of 2 theta, again, reduces to sine of pi. Because the 2's cancel out, we get pi. Sine of pi is 0 times 1/2 is 0. So plus 0. Last one, sine of 2 theta, the same story. We end up with sine of pi after simplifying, which is 0. 0 cubed is 0 times minus 1 over 6 is 0. So all of this, and of course, minus, when you substitute these for 0, you get that 0 as well. Okay, so our result then simplifies to all of this. So let's see. A is equal to pi over 2. So we have, so this is 3/2 a squared times pi over 2 minus pi over 4. After taking the common denominator, we have, what do we have? We have 2 pi minus pi. We have pi over 4 on the inside, right? And then, of course, we can multiply these things. What do we get? We get 3 pi over 8 a squared. So 3 pi over 8 a squared here. All right, so this is the area of that asteroid that we have. Okay, the total area. So after we multiply it by 4, right? So it's all there. And I apologize for things like that and things like this. I will clean these up so they are legible before posting them on Canvas, and also get rid of that. Okay, so we should move to case 3, which is calculating an arc length when the equations of the arc are in parametric forms or parametric form. Okay, so that's what we will do next. So this is the fundamental formula we have, which is basically, we know what our parametric equations will be, so we simply take the derivative of each one and square the derivatives, add them and take the square root and integrate the result from alpha to beta, whatever the limits of integration are at that point. Okay, So this is the fundamental formula. All we have to do now is just apply it to examples. So let's do that. Here's our first example. So we want to find the exact length of the curve given to us by these two parametric equations such that t, or the parameter, varies from 0 to 3. So that's basically tells us the limits of integration. Okay, so let's first find dx dt and then dy dt, right? We're going to need those two in order to find what we need to add or square and then add and take the square root of. We're going to find both of these, dx dt and dy dt. So dx dt, this would be e to the t minus e to minus t power. And then the dy dt is equal to minus 2. Okay, so let's incorporate those two results in our formula. So we have L, length of the arc, going from 0 to 3. And so under the square root, we have dx dt squared. So we have e to the t minus e to minus t squared, power squared, plus minus 2 squared, right? And of course dt. So let us expand this and then simplify the terms here as much as we can. So we have integral from 0 to 3 of, if we expand this, we get e to the 2t power minus 2 times e to the t power times e to the minus t power. Of course, these powers add up because the bases are alike. The powers add up to 0 and we get 1. But let's do that in the next step. Plus e to minus 2t power, plus of course 4, and then dt. Okay, all right. So then we have integral from 0 to 3. So this, instead of that, we have just minus 2 e to the 2t power. We have minus 2 here, plus e to the minus 2t power, plus 4 dt. But 4 and minus 2 all, clearly add up to positive 2. So we get integral from 0 to 3 e to the 2t power plus 2 plus e2 minus 2t power dt. Okay. Now, these three, we can combine them into a binomial squared. So let's do that. So they can be written in terms of a perfect square. So we have square root of e to the t power plus e to the minus t power and then squared, right? If you expand this, you will get this. And then, of course, dt. Okay. Of course, the square root and this power on the inside cancel each other out. So we have integral from 0 to 3 of just e to the t plus e to the minus t dt. These two terms have very easy integration, so we have e to the t integrates into e to the t power, and this one minus e2 minus t power, and of course this is going from 0 to 3. Okay, So then we can continue here. So we have the length of the arc, or length of the curve. Let's substitute for t with 3, so e cubed, and I will put the parentheses here, e cubed minus e to minus 3 power, and then minus e to the 0 power is just, and then it'll reduce to 1, minus e to another 0 power. Like that. And then so we have, let's see, what do we get? We get e cubed minus e to minus 3 power. This is just 1 minus another 1. So that's just adds up to 0, right? This is 0, so we end up with the arc length to be equals to e cubed minus e to minus 3 power. Like that. Okay. Let us do another example. So we have these parametric equations, and we want to find the arc length given that t, our parameter, varies from 0 to pi. Okay? Well, the first thing to do is just find dx dt and then dy dt. Let's do that. Since you've already seen one example, it would be a good idea for you to pause the video, please, and complete this solution on your own, and then return to this to see how we're doing. Are we agreeing or not? Okay, so I'll begin with dx dt. And this would be just minus 3 times sine of t, and then plus 3 sine of 3t this time. Okay, and dy dt would be 3 times cosine of t, and then minus 3 by the chain rule times cosine of 3t. Okay. If you want, you can put these in parentheses because that's the argument of the function. Okay. All right, so let's insert our results into the formula we have. So we have arc length equals integral from 0 to pi, right? Zero to pi, and then we have the square root, of course, and then we have dx over dt squared. So we have minus 3 sine t plus 3 sine 3t squared. And then plus dy dt squared. So we have 3 cosine of t minus 3 cosine of 3t squared. Like this. dt. Okay. All right, so we have, I hope I can fit it all across the page. Maybe I should write a little bit smaller, but we need to expand each of these binomials. So let's do that. Let me well, I should write smaller, otherwise I'm not going to be able to fit it all. So expanding this, we get positive 9 sine squared t. 2 times this times that, we get minus 18 sine of t times sine of 3t plus, of course, 9 sine squared 3t. Okay, plus the rest of this. Let's see. So 9 cosine squared t minus 2 times this times that. Again, we get minus 18 cosine of t times cosine of 3t, and then plus 9 cosine squared 3t. Like that, and then of course dt. Okay. All right. So now we have, obviously there are things that will cancel out. Let's see. So we have 9 sine squared t and 9 cosine squared t. Okay, so we can factor out 9 from those two and then add them, which we get 1 in that case. But let's do that. So let's do that in the steps. So we have the length from integral from 0 to pi, and then so these two, I'm factoring them out. 9 times sine squared t plus cosine squared t, and that, you know, it adds up to 1, right? From trigonometry we know that. And then, of course, we had a couple of terms with minus 18. We can factor those out and put them together. So minus 18, this one and that one. So minus 18 times cosine t times cosine of 3t like that, and then plus sine of t times sine of 3t. Sine of 3t, right? And then we had 9 cosine squared 3t and 9 sine squared 3t as the only two remaining terms. We can factor these out again and write them just like that, with the exception that this time instead of t we have 3t. Okay, so plus 9 times sine squared 3t plus cosine squared 3t. And then close parentheses, and of course dt. Okay. All right, so we know that this is going to be equal to 1. By the same token, this is going to be equal to 1. And check this out. Cosine of t times cosine of 3t plus sine t times sine of 3t. That reminds us of some identities we learned about trigonometric functions. And that was, we can rewrite this as cosine of t minus 3t. Okay, it makes no difference if it's 3t minus t, because cosine is an even function. So whether you have minus 2t or positive 2t on the inside, the result is positive cosine of that quantity, cosine of 2t. Okay, so let's simplify this a little more, given this what we have here. So we have that equals 0 to pi and square root of 9 times 1 minus 18 times all of that, so cosine of t minus 3t plus 9 times 1 again, right? Plus 9 times 1. And this is dt. Okay, so what do we have? 9 plus 9, that's 18. So we have 18, and then minus 18 cosine of minus 2t, right? Minus 2t. And that's it, and then dt. Okay, so let's go to a new page here. That. All right, so at this point we can, I guess we can factor things out, right? So let's do that. So we have, let us do that here. Pi, we have 18. Well, first let me simplify this because, well, let me write this because cosine of x is an even function. Then cosine of minus 2t equals cosine of 2t. Okay, like that. So we're going to replace this with cosine of positive 2t. Okay, dt. And then, so at this point, let's recall that cosine of 2t, these are those identities we learned in trigonometry a couple of semesters ago, right, before calculus 1. So that cosine of 2t is equal to 1 minus 2 sine squared t. Okay, so let us then replace that cosine of 2t with this. So we have the arc length equals 0 to pi square root of 18, let's factor it out, times 1, right? 1 minus, instead of that, we're going to replace that with 1 minus 2 sine squared t, of course, dt. Okay, so if we distribute this minus, we can then cancel out the 1s. And so we have it's 18 times 1 minus 1 plus 2 sine squared t. dt. Okay, so we have these two canceling, and then we have integral from 0 to pi 18 out here times 2, right? Because these two add up to 0, then 18 times 2, we get 36 sine squared t dt. And then of course this square root, we have perfect squares on the inside, so we get 6 sine of t dt. And then we can easily integrate this to minus 6 cosine of t, going from 0 to pi, right? And then, okay, so let's substitute for t with pi and 0. We have, so minus 6 cosine of pi minus 6 cosine of 0. Okay, like that. So cosine of 0 is just 1. 1 times minus 6 is minus 6. Minus times that is going to be positive 6. So what do we have here then? We have minus 6. Cosine of pi is minus 1. Minus 1 times minus 6 is positive 6. And this we already said, it's positive 6 again. So we have the length of the arc equaling 12 units. Like that. Okay. So with this, now we've covered what happens to applying calculus to equations, to parametric equations, when we want to find the tangent line, the slope of it, when we want to find the area under a curve for which we have parametric equations, and what happens when we want to find the arc length when we have a set of parametric equations for the arc. And I hope this was useful and worth your time. If you have any questions, please stop by my office hours. I thank you for watching this video until the end. For now, have a nice day, and I hope to see you again next time.